Hi, this is Professor Cummings, and this is going to be a short video. Actually, it's a series that I'm going to be making starting in 2018 on mechanical design. And what we have there in front of us is a robotic gripper. So it's just an animation of a robotic gripper. And what I want you to take note of is, even though this robotic gripper is a pretty cool looking picture, it actually is made up of different components. And each one of those components is a fairly simple movement behind it. And this is the whole idea behind mechanical designs, particularly something I want to go over today known as linkages. So what we're going to do is we're going to understand what everything in this mechanism is called and how we actually can predict the behavior of this mechanism through a few simple rules that we have at our disposal as engineers when we look at mechanical or designing of mechanical objects. Now, one way you can think of that robotic gripper is just a series of linkages. We saw it had a the gripper that actually picked up whatever it was you're going to handle, and then there were just a couple of rigid bars that were pinned to it, with joints that went back to a gearing mechanism, and as the gearings rotated, it actually created an output that we wanted, which was an actual gripping action. And that is the basis of most mechanisms. They're just a variation of linkages. And you can see here over at the right where we have a piston, which is just a series of bars and a slide with the piston head going up and down, and some sort of pin that keeps the whole thing grounded, and so the motion becomes predictable. Over here to the right of that is an oil derrick. Again, it has a very predictable motion that we want. It actually creates a pumping action going up and down, and it does this again through a series of linkages that starts back here with some sort of an actuator, a motor of some kind that, through a series of linkages and the way they're connected together, creates this particular output. Again, mechanisms are just all variation of linkages. Now, a linkage, if we just define what that is, a linkage is just a rigid body, got that in bold, of any shape that has a number of attachment points called nodes. That's the definition, the engineering definition of a linkage. Now, linkages are connected specifically to have a controlled output. Now, these things have been put together, again, all these are just, rigid bodies being pinned together, held together through nodes to get you a specific output. And the output is controlled. There is a very controlled manner to this piston. If you were to go into designing internal combustion engines, you'd see that that movement inside of the engine is very well calculated, very detailed. And the same goes with this oil derrick. There is a very specific motion that you want to get in order to actually pump oil out of the ground. So the linkages are connected specifically to have a controlled output. From the piston to the oil derrick to the robotic gripper, there's a very specific thing that you're trying to accomplish, a very specific motion that you're trying to achieve with this series of linkages. Now again, this is just a rough example of some linkages. When it's connected at 2 points, they're called binary. When there's connected at 3 points, 3 different nodes, you have a ternary and quaternary link when it's got 4 nodes. And the nodes are just the points where the linkages can be connected. Basically they're holes in the linkage where you actually will start to create the connection. Now, if we look at that piston and that oil derrick, you can see that all the pistons, all the linkages throughout the piston are considered binary. They've basically got holes at 2 ends, all of them, and ternary. And this main one is the ternary, the actual head of the derrick. So it's got a node here at one end, a node in the middle where it actually uses a pivot or a fulcrum, and then there's a node here at the end. 3 functioning nodes, so ternary. And you also notice that in this system there's some sort of grounding point for each one of these mechanisms that connect all these linkages to. And this is you can think of this as the datum point, or just a grounding point for the entire system, keeps it somewhat under control. Now, in order to understand linkages, first I want to go through another concept, degrees of freedom. Now, when we think of a degree of freedom, it's just how much movement an object has to move around. It's the degree of freedom. So it's the number of independent parameters that define its configuration. It is the number of parameters that determine the state of a physical system. Now that's just a fancy way of saying it can go up, down, left, and right. Rigid body diagrams have 6 degrees of freedom. Degree of a rigid body is to go X, Y, and Z, or in other words, up, down, left, right, and front and back. So it can go through the, up, down, right and left, backwards, and forwards. So 3, and then 3 more, so 6 degrees of freedom in total, which are just rotational. And these rotational, again, is, the yaw, going from, rotating in one direction around one axis. The roll, again, rotating about another axis. And then the pitch, which is rotating about yet another axis. So 6 degrees of freedom for a rigid body. Again, you can see this demonstrated through this not really a cube, but a prismatic figure, a rectangular figure. Again, it's got 6 degrees of freedom, X, Y, and Z, and then rotation. In machine tools, we say A, B, and C, theta, phi, and gamma. So up and down, left and right, and front and back. And again, this is the degrees of freedom of a rigid body. Now, I want you to think of that sentence there, or that phrase there, a rigid body. Each one of the links in that robotic gripper was a rigid body. The 2 claw ends were rigid bodies. The links that connected it were rigid bodies, and the gearing system was a rigid body. Each one of those, unconstrained, has a degree of freedom. Now, what's the key here? They weren't truly unconstrained. They had something that constrained them together, something that helped them get to the point from just being a free to move physical body to being something that had a purpose behind them. And those things were called joints. So links are connected by joints. So that also reduces the degrees of freedom. The joints help dictate what that degree of freedom is going to be. So joints, they're characterized by their geometry and the degrees of freedom. Again, so each one of those rigid bodies being connected together by joints are dictated, their degrees of freedom are dictated by the nature of the joints that they have and how they are held together. So with any of these joints, we have, with a linkage mechanism, we have 6 joints that we're going to talk about here. There are 6 immediate joints, and these are a very special joint. These are called lower pairs, and we'll get into a definition of what that is. One is a revolute, which is just basically a joint that rotates about, and this is 1 degree of freedom. Again, when we think of the 6 degrees of freedom, this has 1 degree of freedom, which is a rotational degree of freedom. Prismatic, which is just a sliding, like the piston going inside of the piston bore, back and forth. A screw, which is 1 degree of freedom, again, left to right. Cylindrical, which can rotate, but it also has a degree of freedom of sliding, just like the prismatic, but now it has a sliding motion. A spherical joint, also known as a ball joint, which has 3 degrees of freedom. And planar, which also has 3 degrees of freedom. So those are 6 types of joints, and they help dictate the degrees of freedom that your linkages, which is actually what connects them together, your linkages will have. Now you can see this when we look at a robotic arm. All of those are just very simple joints held together. They're all revolute joints. So each one is a revolute joint. You may see one with a spherical joint, but by and large, the linkages in this particular robotic arm are just revolute joints. It dictates how much degrees of freedom the entire robot's going to have. Again, another look at the piston. Here we can see pistons fall into the category of a prismatic joint. Again, it has 1 degree of freedom, going up and down in this case. And then the spherical joint. Probably seen this in some sort of, a lot of times swings, or if there's a swinging mechanism holding up above, they'll use a spherical joint and allow this thing to go in multiple directions or give it 3 degrees of freedom. Again, these are what characterizes what the movement of that linkage is. And again, remember, a link is about having a controlled output. So these linkages that you select are very important in your mechanical design. Now I mentioned the term of a lower pair. Now let me go back and define that and give some clarity of what I meant by those six. Those six types of joints are a lower pair. So first let me define what a kinematic pair is. It's the connection between two bodies that imposes constraints. Again, constraints, we're talking about controlling what the linkages are going to do. So it imposes constraints on their relative movement. Again, think back to the robotic gripper. You need some sort of constraints, some sort of control over those 6 degrees of freedom in order to control how many degrees of freedom you are ultimately going to have, so you can predict and gauge how that robotic gripper is going to move. Okay, so this kinematic pair is just a connection between two bodies that imposes constraints on their relative movement. So that's just a fancy way of saying a joint. So there's two types of joints, two types of kinematic pairs. Okay, there's a lower pair, two corresponding surfaces in contact between a moving body and a fixed body. Again, another fancy way of saying some type of a joint. So two corresponding surfaces, yellow to blue, or green to blue, however this shows up on your screen, in contact between moving body and a fixed body. So moving body, fixed body, moving body, fixed body. Okay, and again, see how that fits the kinematic area connection between two bodies that impose constraints, degrees of freedom. Then there's the higher pair. A higher pair is a little more complicated, but I also think tend to be a little more intuitive for people to understand when we think about joints. Okay, it's a point or line contact from a curved or point contact between a moving body and a fixed body. So what does this mean? Key here is curved or point contact. So what are we talking about here? We're talking about something that's being influenced simply because it's got curvature coming in contact with another body to help control how it moves. So what's that sound like, these curved point contacts? Well, two things. One is cams. Cams have curves as well as point contacts. A curve to curve is a point contact that controls the movement of two bodies. Whenever you see a cam in this particular instance, you're seeing a linear movement going up and down in a very controlled fashion, dictated by what you designed into this cam. Another good example would be the involutes in a gearing system. These are two curved surfaces. That's what an involute in a involute gears is by definition. And there is a single point of contact at any point that they touch. So this is just the way an involute works. So these are higher pair. Lower pair, where you just got two surfaces sliding against each other or rotating with each other. And here you have higher pair, which is a point or line contact from a curved or point contact between a moving body and a fixed body. So I'll say all that because I want to get you to this point of understanding how a mechanism moves. Now, we described a rigid body. Any link in the system is a rigid body. But when you put those links together, you get a mechanism. And when we think of the degrees of freedom of a mechanism, what we're talking about here is a word called mobility. So the mobility is the degrees of freedom of a device or mechanism, again, versus the rigid body. And the way to understand this is with something called a Kutzbach equation. Now, a Kutzbach equation is just a way of calculating the mobility of a mechanism, an assembly of links and joints. So again, think of our robotic gripper. It's a series of links and joints, and one way to try and understand that mechanism, the robotic gripper, is with this Kutzbach equation. And what it is just saying the mobility is equal to 3 times the quantity of the number of links minus 1 minus 2 times the lower pair minus the upper pair, or the number of 1 degree of freedom points and the number of 2 degrees. So that is just one way, and this is probably the more common way if you think of J1 as the lower pair and J2 as the higher pair of joints. So the types of joints and the number of linkages that are involved is what helps you understand the mobility according to the Kutzbach equation. Now there's a limitation to that, and we'll go over that in a second. But first, let's look at that Kutzbach equation. So what we have here is a mechanism, a piston, that is going up and down, and a still picture of the same piston. And let's go through it and apply this Kutzbach equation to it. Well, first you have to understand the number of links involved, So if we consider the number of links, we've got 4 linkages, and we can see that we've got 1, 2, 3, 4 linkages, and the number of joints. So we got a number of lower pair joints, which is 4. There are 4 lower pair joints, so there's no cams, there's no gearing going on here. So we got 3 revolute joints, and then 1 prismatic joint, which is the actual piston sliding up and down the inside of the chamber. So we have no higher pair joints. So if we apply that to this Kutzbach equation, we can see that we've got 3 times 4 links minus 1, minus 2 times the 4 lower pair joints, and we've got no higher pair joints. So this drops out. Now get my cursor. There we go. So the higher pair drops out, and when we simplify this equation, we end up with 9 minus 8 minus 0, and we come up with the mobility of 1. Now that is for the whole mechanism. You can see this thing is moving all over the place. There's all sorts of movement, but for the mechanism itself, we're just concerned with this 1 degree of freedom. This mechanism has 1 degree of freedom, and it's the up and down motion of the piston. Now here's the limitation of the Kutzbach equation. It doesn't take into account 2 important things. Number 1, what the relative lengths are of the different linkages, and number 2, how they're oriented, how they're assembled together, how they're configured. Okay, so, and those can actually dictate and help change the actual motion of that mechanism, the mobility of the mechanism. So depending on how long the particular lengths are, we can actually change how many degrees of freedom or the mobility of that equation, as well as how they're configured. So let's go through and understand a little bit more about that. So to understand that, there's an engineer named Franz Grashof, and he actually wrote The Theory of Machines, so a lot about machine design. And one of his important discoveries was the Grashof Condition. Now let's go ahead and read this through. If the sum of the shortest and longest link of a planar quadrilateral linkage is less than or equal to the sum of the remaining 2 links, then the shortest link can rotate fully with respect to the neighboring link. Now what does that mean in plain English? What that means in just plain simple terms is that if you've got 4 links, the sum of the shortest link and the longest link is going to be less than or equal to the sum of the remaining 2 links, whatever those 2 links are, that shortest link will be able to rotate in a complete circle. It'll be able to make a full rotation. So he is describing a 4-bar linkage, and that is very important designed in mechanical design. It's a 4-bar linkage. It is a very important mechanism. This shows up in all sorts of mechanical devices, from your windshield wiper to your steering mechanisms to several things that I probably can't think of. So this is the whole idea behind a 4-bar linkage and how you design 4-bar linkages. And this is the equation written out. So you got S plus L, short link plus long link, should be less than or equal to the remaining 2 linkages. And if we look at this little diagram of a 4-bar linkage, what you can see is the sum of the short link, the green, and the black link, the longest link, is actually less than or equal to this red and this yellow. Now if you were to take these out and lay them out longer, it's pretty intuitive that when this green link is laid out horizontal, this yellow and red would still be longer than it. So the Grashof inequality holds true, and the shortest link can fully rotate with respect to the neighboring link. So that is the Grashof condition and the Grashof inequality. So let's think about the motion of the 4-bar linkages. Now it's dictated by 2 things. Now the Kutzbach, didn't take these into account. So the Grashof actually does. So it's dictated by the lengths of the linkages, hence the Grashof inequality, and the inversion or configuration of the linkages, how these linkages are actually configured together. And as you can see, if we look at these two links, and we already labeled them by Grashof's terms, short link, longest link, and P and Q represent the other two linkages. There are several different configurations or linkages that can be fixed, whether it's the shortest link or the other remaining links, and you can end up getting all sorts of different motions out of it. So again, let's look at this Grashof link just based just on the inequality. How does this affect things, this equation? If the Grashof inequality is false, first thing we know, if that inequality is actually false, in other words, if the short link and the long link are actually summed together greater than the other two links, then it's a non-Grashof linkage, and none of the linkages will make a full rotation. And you'll end up with a situation like this, where all you're getting is reciprocation. The linkages are just reciprocating back and forth. Now, if we look at Grashof and see his equality is true, then you have what's known as a Grashof linkage. And that is saying that this equality is true, you will see something make a complete rotation. Now, of course, this other linkage here, this particular blue one, is actually making a reciprocating back and forth, which is actually, a pretty important concept. And if you look at this lower image, this lower animation, doesn't this look a lot like how a windshield wiper works? You have something that rotates, probably with the shortest link underneath the hood of the car, and up here where the wiper blade would take place, you're swinging back and forth. This is the cleaning motion of a windshield wiper. It's a Grashof linkage, a 4-bar linkage. Now again, let's look at this a little bit more. Now if we have the still picture and then we have it animated out, again we can see how this, hopefully you can see how this looks more like a windshield wiper motion, where we got the shortest link next to a fixed link, and we got the longest link, and you're getting this complete rotation, and then you're seeing this rocking motion on this one. But let's go through a few things. Now all these linkages have a name. First, the fixed link is known as the ground. So it's grounded, it's rigid, it's not going anywhere. It's what helps maintain the control of the entire system. The second link is known as the input link. This is where the motor or actuator, the actual movement is being actually driven through this particular link. In this case, it's the shortest link. So it's connected to some sort of an actuator. And you've got the coupler, and this link actually just is connected between that input and your final linkage, so also known as the output, which is the fourth link. And that just gives you your desired motion. And that output is either going to rock, it's going to oscillate, and that's when we call that a rocker, or it's going to make a complete revolution, which makes it a crank. And of course, that term, crank and rocker, also applies to your input. Now, as far as how they actually are configured, are the inversions, the Grashof's inversion. The good definition of that is the fixing of a particular linkage within the mechanism. Now let's look at that. When you have when either the links are adjacent, the shortest link, the ground link is fixed, you end up with a crank rocker condition. So here we have the ground is adjacent to the shortest link. We end up with a crank, the complete revolution, and a rocker condition. Again, that has certain purposes to it. Again, your windshield wiper is a good example. When the links opposite the shortest link is grounded, again, this is a different type of configuration. So you got the shortest link, and the link opposite that is the grounded one. You end up with a double rocker. So nothing makes a complete revolution, neither the input or the output, and what you end up with is two rockers, a double rocker. And then you've got a double crank. That's what happens when you ground or keep fixed the shortest link, in this case the red. And what you end up with is the input and the output are both making complete revolutions. So that is known as the double crank. So we've covered, how the The lengths of the linkages affect motion, as well as how the configuration of the linkages can affect the motion. Now there is one linkage, a non-Grashof linkage, that I want you to take into account. And this one, this is where the sum of the shortest link and the longest linkages are actually equal. So S plus L is actually equal to P plus Q. And you end up with this particular condition, which is just a parallelogram linkage. You can see you're seeing a complete motion in this particular picture, but that's not always the case. There's actually something to this particular design that is very curious. You know, its motion can become indeterminate, or another way of saying unpredictable, when the links are collinear. Now what collinear simply means is when all these linkages completely line up, and they completely line up when they're in the horizontal in this particular orientation. And that lineup is called a change point. Now what does that mean that they're unpredictable? Well, the picture we're showing is two complete rotations, but when you've got a parallelogram linkage, it's also capable of doing something else, which is actually becoming a rocker scenario. You know, at that change point, when everything is lined up in a collinear fashion, it is possible that that can take on an unpredictable motion unless you find a way to control or constrain it. But even without that, this is still even so, this is still a very, very important design of a 4-bar linkage. And let me show you. If you take this and put a fixed point or control the motion of how this thing is going to rotate, you can actually use this in a lot of different applications. One is locomotion wheels. If you notice in the back, you've got a 4-bar linkage. And it's not just a 4-bar linkage, it's a parallelogram linkage. And the way it is actually controlled is through the linkages before it. Going back to this end, what does this actually do? It actually makes sure that when you're at this collinear change point, that you don't have an unpredictable output. So you've got a series of linkages controlling the 4-bar linkage. Another example is steering wheels, or the steering mechanism in a lot of cars. In this particular case, and they're not always the case like this, you have a parallelogram linkage. You know, so again, this equality holds true. And as you can see, this was typically, the yellow bar is typically your input. It goes from left to right, and that's how you rotate your wheels to make sure you can make a turn. So just to summarize everything up, a 4-bar linkage is just 4 binary links connected by 4 pin joints, 4 types of pin joints. The behavior of the 4-bar linkage is based on the relative lengths as well as the different types of configurations of the 4-bar linkage. So you can see here we've got different lengths and different configurations. And the Grashof criterion makes it possible to predict the behavior of the mechanism. And this is the Grashof inequality. The short link plus the longest link is less than or equal to the remaining 2 linkages. So this is Professor Cummings. I hope this was useful to you. And I'd like to thank you for watching. And if you aren't subscribed to the channel, go ahead and subscribe. And I'll be putting out more videos in this series. Thanks a lot.